In this short video, I'll be presenting multi-agent active search, a reinforcement learning approach, joint work with Romina Godz and Jeff Schneider. In many applications, from search and rescue to reconnaissance, it's becoming common for teams of robots to work together to search for targets of interest. For example, following Hurricane Harvey in 2017, over 400 drones were volunteered by local Texans to help with situational awareness. Unfortunately, pilots face significant challenges in effectively coordinating these drones. Examples like this illustrate the need for coordination algorithms to manage robotic teams. In particular, in this work, we focus on the multi-agent active search task, or MAAS, a collaborative active learning problem with the objective of locating sparse targets in an unknown environment. The main idea behind previous MAAS algorithms is to model unknown targets as a latent sparse signal, which agents can noisily observe through constrained linear sensing. Agents then use their dataset of observations, DT, to form a posterior belief state, BT. This belief state represents the agent's uncertainty about the underlying sparse signal. A sensing action, AT, is then selected by optimizing an acquisition function over all candidate actions. Different algorithms propose different acquisition functions, and each typically requires approximating the solution to complex integrals for every candidate action. Although these algorithms are well motivated from a theoretical perspective, they are limited in a few important ways. Firstly, by relying on online integral approximations and exhaustive search over action space, previous algorithms place an enormous compute burden on agents, often taking several minutes to determine a single sensing decision. Additionally, as we demonstrate in our paper, previous MAAS algorithms are suboptimal from a decision theoretic perspective. Different algorithms introduce different biases inspired by other work in active learning or search, falling short of true Bayes optimal performance and inducing myopic search behavior. We address these issues by formulating the MAAS problem as a single-agent POMDP, or, equivalently, a belief space MDP. This MDP describes the decision problem faced by a master puppeteer that centrally controls all agents assuming perfect communication. Here, the belief state is obtained using observations collected from all agents. The action corresponds to a set of sensing locations, one for each agent, and the reward can be specified in terms of information theoretic quantities derived from the belief state, such as the posterior entropy. We use PPO to train a cheap feed-forward neural policy within this MDP. This offers several advantages over prior work. Firstly, it allows us to obtain an efficient, centralized policy that maps from a shared belief state directly to sensing actions, significantly reducing the online compute burden. Secondly, by design, DeepRL allows us to optimize for truly non-myopic objectives by encouraging behavior that achieves good performance throughout the entire trajectory of search. We show how DeepRL achieves state-of-the-art performance on centralized MAAS tasks while simultaneously achieving significantly less online compute at test time. Although this formulation is appropriate under full communication, real-world tasks typically suffer from unreliable communication channels. We therefore describe an approach that leverages common shared beliefs during training and local beliefs during testing. This avoids the need to use more involved multi-agent DeepRL algorithms. We show that policies obtained using this approach are surprisingly robust to unmodeled test time miscommunications. We provide theoretical and empirical arguments to explain this result. In short, for certain MAAS problems, optimal multi-agent sensing behavior involves significant sensing overlap amongst agents, which naturally safeguards against potential blind spots. In summary, we argue that DeepRL is a particularly strong choice for real-world active search tasks, both from a decision theoretic and computational perspective.